Good morning, good afternoon, or good evening. This is a full paper workthrough of the Step 3 2024. We have reached question 4 on this playthrough, on this walkthrough. As always, you should only really be watching this video if you've already tackled the question, and you're either looking for some hints to help you finish the question or looking for another way to think about some of the processes involved. This is question 4. This is a more geometry style question, so one that I personally would have avoided when I was doing STEP at the time, but we'll have a go at the question anyway. So to start off, we are told about some angles between straight lines with certain gradients, and we want to show that those angles are, if those angles are 45, then there's a special relationship between the two gradients. And this is actually a really useful general fact that it's worth having in your toolbox of techniques. And that is that the gradient is actually linked to the angle with the positive x-axis. So if I draw myself two lines and I put in a positive x-axis here, if this first line is, let's say, y equals m1x plus c1, taking a hint from their notation, I've just put a c1 and a c2 on. We've been told that this angle here is 45 degrees, but I'm also going to label on this angle as theta 1 and this angle as theta 2. And the really nice fact is tan of theta 1 is opposite, which is a change in x, over adjacent, which is a change, opposite, which is a change in y, over adjacent, which is a change of x, is exactly the gradient. And similarly, tan theta 2 is exactly m2, and we've been told that theta 2 minus theta 1 is 45 degrees. Well, hopefully you might even recognize the shape of the answer they're giving us. Something minus something over 1 plus the product of those things. That actually should remind you of the double or the addition formula for tan. So I'm going to first recall that tan of A, and I'm actually going to put A minus B because that's what causes the top to be a minus and the denominator becomes a plus. Let A be theta 1, B be theta, no, I want that the other way around. I want A to be theta 2, B to be theta 1. So that's going to mean that tan of theta 2 minus theta 1, which is 45 degrees, equals tan A, which is the M1, the M2, minus the M1. And you might be looking and being a bit worried that's the wrong way round, as I was just briefly. But we actually have two pictures going on. So this equals 1. And it's basically to do with the signs of these angles. So we actually could have had y2, the angle between y2 and y1, creating an obtuse angle between them. So we have an extra right angle here. So really we have theta 2 minus theta 1 equals 45 degrees or 135, or it could actually be 225 and 315, but then if you've got the reflex angle, you can just turn it back into an acute or obtuse, because of course tan is periodic by 180. So that really means Down here I should have, this is either tan 135 or tan 45, depending on the situation. And that exactly gives us the tan 135 gives us the possibility of -1 or 1, which then we can collapse together. We can swap the sign because our answers are plus or -1 anyway. So swapping the sign on the left gives either plus or -1, depending whether the gradients were in line with each other or against each other. If they're both positive, both negative, or one was positive, one was negative. Okay, we've got that result. Part 2, we're now introducing a parabola, a quadratic curve. The curve C has equation 4a y equals x squared. So that's just going to be a quadratic with a repeated solution at 0, but it's been scaled downwards by a factor of 4a. If P does not equal Q, show the tangents to the curve at the points with those x coordinates, meter to next coordinate of. Find the y coordinate in terms of. Okay, so we have ourselves this parabola. We're saying P and Q are different. So there's some P here, there's some Q here. So this is going to have coordinate. Well, if the x coordinate is P, subbing that into the equation here, we'll get the y coordinate is P squared over 4a. And similarly, this will be Q squared over 4a. We want the tangents at these 2 points, and we want to end up intersecting them. So to find tangents, we need to find the derivative and therefore the gradient. So dy by dx is going to be x over 2a. The 2 that spawns cancels down with the 4. So then I'll call these points capital P, capital Q. At P, the gradient therefore is going to be P over 2a, which means the tangent at P, which I'll call TP, is going to be y minus the y coordinate equals mx minus the x coordinate, and the m we do actually know as P over 2a. So then y is going to be equal to P over 2ax. I'm going to have a minus P squared over 2a, and I'm adding a P squared over 4a. Already this is 2P squared over 4a, so that comes out as minus P squared over 4a. And we could do the whole work again, but it's all symmetrical in the P and the Q. So similarly, TQ is going to be y equals Q over 2ax minus Q squared over 4a. We're trying to find the x coordinate. So these will intersect when... and we can basically put the 2 equations equal to each other because I've got P equals in both cases. Px over 2a minus over 4a is equal to qx over 2a minus q squared over 4a. Things that will be quite helpful to do. Let's put all the x's on one side. I think I actually want to first multiply by 4a. That's going to be 2px minus p squared equals 2qx minus q squared. Let's rearrange this a little bit. This is going to be 2x lots of p minus q equals p squared minus q squared. As soon as you see the dots, instinctively you should be looking to factorize, or at least have the option of factorizing. And you can see that factorizing here is very useful because the p minus q's cancel, provided the p minus q is non-zero. And that was the case because we've been told that p was not q. So we're allowed to cancel only because. So x is that value there. Now the y value, we need to sub this x back into either of our originals. So let's sub into TP. So y is going to be equal to, and now this is going to look a little unpleasant, p plus q over 2 is what I'm subbing in, minus the p squared over 4a. I'm hoping this comes out really pleasant and symmetric. It kind of looks like it's going to be. So it's going to be a p squared over 4a plus pq over 4a minus p squared over 4a. The p squareds over 4a's cancel. I'm left with that. So we intersect at p plus q is my x coordinate and pq over 4a is my y coordinate. A couple of things just to notice from that. Firstly, the p and q are symmetric in both coordinates. That's quite pleasing. We didn't say anything special about the p and q. So they should be symmetric. If I swap them over, this hasn't changed. And the other thing to notice is the a only appears in the y coordinate, which if we look at the equation of the curve makes sense because that a is attached to that y. The x isn't impacted at all, which is quite pleasing as well. And if you do think of how that 4a appeared in terms of a enlargement, that also makes sense. If you consider the curve just y equals x squared and turn that into 4ay, then it's the y coordinate which is being scaled by a 4a, which looks exactly like what's happened here. Okay, so we have that done. Show further that any two tangents to the curve which are 45 degrees to each other meet on that curve. So now we want to show that condition provided that they meet at 45 degrees. So that looks like we're going to apply part I. So meet at 45 degrees implies this m1 minus m2 over is plus or minus 1, where the m1 and m2 are the gradients. Well, we have our gradient of the two separate conditions as those two things there. So the first part of the question is implying if I subtract them, p over 2a minus q over 2a is 1 plus pq, no squared there, pq over 4a squared is plus or minus 1. Now the plus or minus is a little bit awkward and it's not immediately obvious how I'm going to convert that back to an equation in y and x. But let's simplify this. Let's see how it's going to be made more pleasant. I'm going to times top and bottom by 4a squared because I really don't like having those fractions in there. This is going to be 2a survived on the top over 4a squared plus pq is plus or minus 1. Plus and minus is still not pleasant in my mind. How do I wish to rearrange this? Do I want to rearrange this to make it equal to 0? I'm starting to see that there might be some factorization that could go on. This is going to be plus or minus 4a squared plus or minus pq. This does feel like there's going to be, because this thing here is p times q, this is 2a squared. Well, this is a 2a and a 2a, so it's quite plausible that this could factorize in some cases. Alternatively, I could use this to write what PQ is. and put the PQ in here and try to show that this X and Y that are now slightly more linked together satisfy that equation. In particular, really, it's destroying it. We're trying to get rid of the P and the Q. Probably the best bet. I don't like the plus or minus. I think I'm going to do that second thing and rewrite the X and the Y using this condition here. And the plus and minus is awkward, but we'll just do it. Let's see what happens. So I'm going to write this as plus minus PQ equals, actually I don't want to put the plus or minus in front there. So the PQ, I'm going to move that to the other side. So this is going to be 2a P plus minus Q minus plus 4a squared, and then I'm going to divide by the plus or minus. So that basically swaps us, well, puts the plus or minus there. If I'm dividing by the plus, it does nothing. And then I'm on the other one, this is going to always be a minus. So it was minus plus. If you divide by the plus, you were using the minus over there, so it stays the same. If you divide by the minus, then you were using the plus, so it swaps. So that always comes out as minus 4a squared. So then we can say a bit more over here. So we intersect when x equals p plus q over 2, and when y equals this whole thing over 4a, well, that's going to have a minus a on the end. Dividing the first part by 4a is plus minus a half p plus p minus q. That looks like it's actually made it worse. I've now got more ugly, unpleasant looking stuff, but maybe this will help me out. I want to show that that any two tangents which are 45 degrees, which are two tangents which lead to this intersection point, meet on that curve. So if you meet on a curve, then when you sub in, you get the equation of that curve. So basically, I want to check that when I sub these things in, all of the P's and Q's cancel, or are the same on both sides even. So I'm actually going to consider something a little bit different. I'm going to consider, and I want to get it to a point where I can just cancel everything. So I'm going to consider this thing, and I would quite like everything to cancel out and be left with just 8a squared. The plus and minus is still a little awkward. I haven't been told anything about the signs of P and Q, so I can't break down to whether it is both gradients positive, both gradients negative, to get rid of one of the plus or the minus. I'm going to sub this in and see what happens. So this is going to be now a half P minus Q plus 3a, so it's going to be a plus 2a. I do need to keep the plus or minus for now, squared, minus P plus Q over 2 squared. I don't have a huge amount of working space. I'll turn the page in a moment. I'm hoping this comes out quite pleasantly. So this is going to then be a quarter P minus Q squared. When I square the first term, the plus minus there does disappear. When I multiply the two terms, I'm going to get plus or minus 2 lots of, and now that plus or minus on there is the one that I'm not happy with, because that can't just cancel unless I have to use this condition over here again Yeah, maybe. Because that plus or minus, we have also that 4a squared plus pq is equal to this plus or minus 2a. We need to be a little bit careful because we're following these plus or minuses around in a weird, almost circular manner. So that brings up the question whether I should have left this y as it was, and maybe something could have come out later. I'm actually... Do I want to do that? I think I want to do that. I think I want to leave this y as it was and then use that new condition later on. So this y in here is going to be slightly simpler for now, and then I'll decide how I want to use it later on. So I'm going to leave this as pq over 4a. So it's going to be pq over 4a plus 3a. And then when I expand this out, I'm going to hope things are more pleasant later on. Plus, this is going to be 3 over 3pq over 2. The a's cancel, and because there's two of them, the 3/4 becomes more pleasant. Plus 9a squared minus, and because I've expanded that out fully, I probably should expand this out fully. P squared over 4 minus pq over 2. Again, expand this out slower if you are, if you need to. And now I'd like this whole thing to cancel down to just 8a squared. So I really need everything except for this to become negative a squared. And the thing that I have over here linking my stuff together, now it doesn't have the plus or minus in it anymore, which is a little unfortunate. There's only one term that comes together. No, maybe this is okay. So let's simplify what we have that can simplify. And I'm now thinking about how I'm going to get to that other condition. In particular, I actually want to use that condition squared. So I'm going to have a minus 4 on this. So I've got p squared. These two simplify to be a plus 1. So that's going to become plus 4 or minus 4 pq. I am going to have another check of that in a moment. This hasn't quite done what I wanted, because I would have liked to have this thing over here squared. So let me check my mental arithmetic. Those two terms are going to become a plus pq, which when I factor out the minus 4, minus a quarter, sorry, is what I'm factoring out, not minus 4. When I factor out the minus a quarter, I do get minus 4 pq. That's not quite what I wanted. If I do look over to this, if I continue manipulating this expression and I square both sides, this is going to be a 4a squared p squared minus 2pq plus q squared. I square the other side, 16a squared plus 8a squared pq plus p squared q. Some of these terms will cancel out or will do something. And I really do, I have really ruined the amount of space I have here. So what I'm going to do, I'm going to get rid of some of this. This is the advantage of doing it on a screen and on an iPad style device rather than doing it on paper. But this is what you use your scrap paper for. A lot of this at the moment is exploration. So I'm going to square it up here. P squared minus 2pq Fortunately, if I undo it, does way more than just my last action. And the point of squaring is really to get rid of the plus or minus. When you square something, it just makes it nicer. Plus p squared q squared. And now I'm noticing that I've got a minus 8 a squared p squared and a positive 8 p squared a squared p squared, so I can bring them together. And again, I'm thinking the best way to do it, I could divide through by 4a squared. Let's divide through by 4a squared. Because I know on the other equation that I do have a fraction that's a little bit similar. Plus 2pq plus p squared q squared over 4a squared. I was thinking about this term here when I justified doing that. So how am I going to use this? I can write this thing equals, so I can replace that term. That seems like the most sensible right now. So let's say that p squared q squared over 4a squared is equal to p squared minus 4pq, as I've moved that term over, minus 4a squared. And if you are playing along at home, you may have spotted exactly how this is going to be useful. So this is now going to be equal to a quarter of the expression on the side, minus 4a squared. Because it was over 16, then we only had it over 4. Plus the 9a squared minus the quarter. And as mentioned way earlier when we saw this 9a squared for the first time, we said we want this all to simplify down to just a minus a squared, and it does. That term's cancelled with that, that's cancelled with that, that's cancelled with that. I'm left with a quarter of negative 4a squared, which equals 8a squared. So thus, the intersection point lies on, just got enough space, y plus 3a squared equals 8a squared plus x squared. Okay, nice. Quite a heavy algebra. Luckily it wasn't too geometric, at least for my liking. But now we're on to part 3. Part 3 of the question now has show that the acute angle between any two tangents to the curve which meet on the curve that is constant. Show that the acute angle between any two tangents which meet on that curve is constant. Okay, so we're kind of comparing what we did in the first part, where we said if it was 45, it landed on this curve. And now we're saying it's landed on this curve. What is the angle that we care about? So we're kind of undoing the work we've done both in part 2 and part I to try and find that angle. Okay. So if the angle between the two curves was not 45, but was theta, then we can get a similar condition for that subtraction. So I think I want to do that first. So if the angle between is theta, then similar to part I, we have the m1 minus m2 over that, which in part I, if you remember, that condition equaled tan of the angle, or 180 minus tan of the angle, because of the acute or obtuse cases. So this thing is equal to either tan theta or tan 180 minus theta. But if you use a bit of symmetry from the tan curve, this is equal to plus or minus tan theta. So what I care about is trying to find this tan theta. So I want this expression here. And now that was quite a weird expression in terms of P's and Q's, because our two gradients were P over 2a and Q over 2a. So this is going to be tan theta is P over 2a minus Q over 2a over this 1 plus PQ over 4a squared, which is, if I simplify in the same way that I've done before, it's really that expression there that I would like to work out. Show that the acute angle, now that two coordinates, also we've been told that the half, was it P plus Q? Yep. Half P plus Q, PQ over 4a. I'm looking at this intersection point that we found in part 2 of the question. Over 4a lies on y plus 7a squared equals 48a squared plus 3x squared. Okay, I lost a plus or minus on that line above. Okay, so that lies on that curve, and I'll quite like an expression with this 2a p minus q over 4a squared plus pq. The only sensible thing, well, first we need to show that the angle is constant. Well, the only way to show that it's constant is to show that this expression here is constant. So let's sub in the intersection point into this curve. Let's try and get an expression for P and Q that's a little bit more manageable. Well, right now we don't even have any relationship between P and Q. Plus 3 over 4. I'm going to square out that straight away. Okay, so I can expand everything out. I'm hoping to get something like that expression, but right now I'm a little bit doubtful. Over 16 plus, this is going to be 7 over 2 APQ plus 49a squared equals 48a squared plus 3/4 p squared, 3 over 2 pq plus 3 over 4 q squared. I'm going to keep referring to what I want to create. So I would really like a p minus q times by an a. Well, right now the only a's aren't in the most pleasant positions. I also want to somehow divide by a 4a squared plus pq. So I want I ideally want some number times 4a squared plus pq equals 2a times p minus q. I think that's what I'm aiming for the most. And there's quite a lot of barriers to that at the moment. Things to collect together. I do think I want to multiply through. Do I want to multiply through by 16? Or do I just want to multiply through by 4? And the debate there is because these two cancel to be an a squared, and I want a 4a squared. I think I still want to multiply through by 16 though, and then I'll divide through by a 4 later on. This is going to be p squared q squared plus, if I times that by 16. I'm going to bring that 48a squared over, so I've got 16a squared, and I'm timesing all of that by 16, so that's going to be 12p squared plus 18pq plus 12q squared. So I almost have my 4a squared there. So let's put stuff hopefully onto the right sides. I haven't lost an a squared somewhere, have I? No. Suddenly thinking this should be 16a to the 4, so I can actually have the square of this fraction rather than the fraction itself. But unfortunately not. Well, maybe fortunately. Oh, I have lost this a here. There's an a on the denominator of that. So this is an a squared on the denominator here, and there is no a on that term. Okay, that does, I think, actually make my life easier. Maybe. So there's no a on that term. And the reason I'm half thinking it's making my life easier is this thing here can now collect exactly with that thing. Okay, that's slightly annoying that I missed that, but let's play forward. That also does give me the a to the 4 that I was half considering might be present in some way. Do I want to multiply it up by that a squared now? Maybe. Let's collect those pq terms together. Let's multiply it up by that a squared. So I'm going to have a p squared q squared, which does really look like the square of this thing, plus 16a to the 4 equals, and I'll have this side as a factorised with the a squared. I had 18 and 56, so I'm subtracting those off. That leaves me 40, 38. Yep, so this is going to be minus 38pq. I'm doing that calculation again in my mind to hopefully make sure. Plus, okay, so I moved the 56 over. I then multiplied up by the a squared. So I would really like things to factorize in really pleasant ways now. This left-hand side, I want it to be the 4a squared. I want it to have the p squared plus q squared. But if I did square that thing, I would want an 8. I want an 8a squared p q in the middle. So I have to add that onto this side, which means I'll need to add it onto this side as well. So that's minus 30pq plus the 12q squared. So that left side is indeed the square of what I want. The right hand side, I wanted to just be p minus q squared, or a multiple of it. But p minus q, I'm actually going to do that little thing up here to see what I'm actually looking for. So this means that tan squared theta is equal to 4a squared p squared minus 2pq plus q squared over 16a squared plus 8a squared pq plus p squared q squared. So that's what I'm aiming for, and that's what I've got on the left, provided my mental arithmetic wasn't too bad. I'm just checking once again. Yeah, it's giving 38. I've added the 8 onto the left, so I need to add the 8 onto the right term on the right. Now I want to factor out I want to factor out a 4 from this side. Well, more than just a 4. I could factor out that 30 is really not... I'm really not liking that 30. It makes me feel like that 30 is definitely wrong in some way. Where could that have gone wrong? So that's coming from the PQ terms. The PQ term is here, which came from multiplying the two terms together, and there's 2 of them, so I double it as well. And the PQ term here, which is from the 2PQ times by 3/4. Now I could have subtracted off first, which would be leaving me with, what is 3 over 2 times 16? Not 18, which is what I put. So there's my error. Let's get rid of those. Highlighting this thing here. 3 over 2 times 16 is 24. So then this, when I subtract off the 56, is minus 22. Nope, 32. And then when I add 8 to that, gives me minus 24, which is really what I wanted. Okay, so that gives me a common factor of 12. So this is 12a squared. That's going to give me exactly p minus q squared in here. So let's continue rearranging. I wanted it to be a 4 on the top. So I can say this is a third equals 4a squared p minus q squared over 4a squared plus pq squared, which is exactly tan squared of the angle between. So that means that tan of the angle between is is plus or minus 1 over root 3. So therefore the angle between the tangents is tan inverse of 1 over root 3. So the root 3 triangle is 2, 1, root 3. So that's this angle up here, which is the 30-degree angle, is 30 or 150, i.e. the acute angle. Because of course, if you have 2 lines where it could be 30, then, or just considering the angles, the lines in the other direction gives you the 150. So this is still fine. Why did it want to undo that much? I.e. the acute angle is constant at 30 degrees. You can kind of see now how we undid for I and for double I in this for triple I. And that's actually quite surprising, in my mind at least, that a 30-degree angle gives you a relatively pleasant intersection curve. It's not surprising that 45 degree was nice. 45 degrees is always quite nice. But 30 degrees giving you something quite pleasant does feel a little surprising, and makes you wonder what other angles could have led to a pleasant looking parabolic-ish, well, it's not parabolic, it's circular, isn't it? No, it's hyperbolic, isn't actually, because when you move that 3x squared over, you've got a y thing squared minus an x thing squared. So we're landing on this hyperbola of some form. Does every constant acute angle between the tangents lead to a hyperbolic locus of intersections? Don't know. But that's probably what this question, or how this question came about. Someone was researching that idea, came across these nice curves and thought, hey, let's put them into a step question. Anyway, that is the question completed. Turned out to be relatively pleasant, more algebraic than geometric in the end, and hopefully quite useful to you. Do continue watching the rest of the playlist for the other questions in this paper.